Hello, welcome to this presentation in Internet of Things and Arduino. The presentation will cover the development and simulation of an AirHeater system developed with Arduino. The system consists of three main components. The control application, which is run on the Arduino board. This works as the controller for the process application and uploads the process data to the cloud storage. The process application is developed on MATLAB, which simulates an AirHeater, while the cloud storage is in thingspeak. The Arduino have two-way communication with Labview application through USB, which is run on a separate computer. The Arduino is connected to a Wi-Fi hotspot and uploads data to the cloud storage. Two libraries have been developed in order to give control application a better structure. The Arduino R4 Wi-Fi board have been used to create this system. As mentioned, the interfaces used is serial communication through USB-C and Wi-Fi. The control application have been developed in the Arduino IDE editor, as seen here on the right. Several libraries are included in the control application. From top down, the application set the parameters for the control and filter libraries, initiate global variables, start communication with the interfaces in the setup. In the control loop, the set point and current temperature from the Labview application is retrieved. Then use the PIC and the LP filter, which sends back a value for the intended voltage for the AirHeater. Every 60 seconds the temperature is sent to thingspeak. By utilizing libraries such as these, the structure of the code is better. It allows to reuse the code in different applications and also makes it easier to distribute the code. The low-pass filter that was created have been tested on a small-scale system with the TMP36 unit. The graph shows the analog data from the temperature sensor and the result after the data has been filtered. As seen, the filtered graph is much smoother and eliminates disturbance in signal. The Labview application consists of two screens: the graphic user interface, which works as the user interface, and the block diagram, which is the logic and implementation of the application. Together, these simulate an AirHeater. The user interface consists of two graphs, one for the simulated temperature out from the AirHeater and one voltage output from the controller. Also, there is a bar to select the set point of the AirHeater. When looking at the block diagram, the application works like this. First, a COM port is selected. The simulation has been set up with initial values which represent room temperature. This is then written to the COM port. Then the output from the COM port is read, which is the result of the control application, and then given back to the AirHeater simulation. Here is an example of the AirHeater simulation. The simulation is started below room temperature. Then the voltage remains at 0, since the AirHeater is not able to cool the room. When the set point is set up, the voltage is adjusted and after a while stabilized together with the temperature. As we see, there is response on the voltage, and we will fast forward. As we see, the voltage and the temperature have stabilized. thingspeak have been used as a cloud and online storage for the data. To set up thingspeak, one must initially create a user account, which require a password and username. In order to store data, channels are created which have unique IDs, possibilities to make these private or public, and unique write and read keys, which can be generated on demand if a new one is required. It is also possible to import and export data files in CSV format. In general, the ID is to protect the system from all digital attacks. In the control application, a separate file is used which contains the SSIDs, password and channel keys. This allows for this type of sensitive data to be stored in a safe file or folder. For thingspeak, the channels requires both unique IDs for writing, reading, and separate IDs for each channel, as well as a user account to access the channel. Security in IoT solutions is crucial due to many potential threats, which can include malware, stolen confidential data, access removal or ransomware, system corruption. Different ways to prevent digital threats is access control, passwords, firewall, backups, education, antivirus software, encrypting, security updates. To conclude, some security measurements have been implemented into the systems, but there are possibilities to implement more. The AirHeater was simulated successfully together with the control application on the Arduino. This is good practice before using the control application on real instruments. The thingspeak storage for this small-scale system works well, with very good security opportunities and data logging, presentation, and data extraction. Thank you.